10.2 Lesson 3, Plane Curves and Parametric Equations. The objectives for today's lesson are: 1. You'll be able to use Desmos to graph the curve represented by a set of parametric equations. And 2. You'll be able to eliminate the parameter in a set of parametric equations. Vocabulary that we've been using: rectangular equation having x and y, parameter. The parameter in a set of parametric equations could be t or theta or even a different variable like s. Graph and curve. We talked about the distinction between the two. The curve is not just the graph, but it includes all of the other information given by the set of parametric equations, such as the direction in which the graph is traced, or the direction in which the curve is traced, called the orientation, also the rate at which the curve is being traced, etc. And if the set of parametric equations represents an object that's in motion, it could also tell us where the object is at a particular time, as we will see in one of our lessons today, eliminating the parameter. So the instructions that we have are: use a graphing utility. We'll use Desmos to graph the curve represented by the parametric equations, indicate the orientation of the curve, eliminate the parameter, and write the corresponding rectangular equation. So number 21, this is our set of parametric equations. X is equal to 4 times sine of 2t, and y is equal to 2 times cosine of 2t. Now, we'll look at the part with the graphing utility second, but first let's go ahead and take a look at how we can eliminate the parameter. We can eliminate the parameter by using a trigonometric identity to help us. So notice that you have both sine and cosine, so that clues you in that maybe you will be using the trig identity sine squared t plus cosine squared t is equal to 1. So that's a Pythagorean identity. So thinking that we might use that, we can begin by isolating sine of 2t and cosine of 2t in our two parametric equations. So we divide the first parametric equation by 4 on both sides, and we divide the second parametric equation by 2 on both sides. Now we're ready to square both sides of each equation. So for the first equation, when you square the right side, you get sine squared 2t. When you square the left side, you get x squared over 4 squared. The second equation, when you square the right side, you get cosine squared 2t. When you square the left side, you get y squared over 4. And this Pythagorean identity, you can use that as long as you have sine squared and cosine squared and the arguments are the same. So you can see that the arguments are both 2t, so we're able to write sine squared 2t plus cosine squared 2t by this Pythagorean identity would be equal to 1. So now we can substitute for sine squared 2t. Sine squared 2t is x squared over 16, and we can substitute for cosine squared 2t, it's y squared over 4, and that's equal to 1. So we have successfully eliminated the parameter. We no longer have t, and we have an equation in terms of x and y alone. In other words, we have a rectangular equation. So if you take a look at that, we just took care of the last part of the instructions: eliminate the parameter and write the corresponding rectangular equation. That's been done. So use a graphing utility. We'll use Desmos to graph the curve represented by the parametric equations and indicate the orientation of the curve. Do you really need a graphing utility for this particular problem? You don't really need it. You can do it by hand. You can use the rectangular equation to have an idea of what the graph should look like. It will be an ellipse. And you can also, if even without the rectangular equation, you could make a table of values using your set of parametric equations and plot points to get the graph. So we'll do that briefly, and then we will take a look at how to do this using Desmos. So when you look at the parametric equation for x, it is 4 times sine of 2t. So if t is equal to 0, then you'll have 2 times 0. So you have sine of 0, which is 0, and 4 times 0 is 0. If t is pi over 4, you have 2 times pi over 4, which is pi over 2. Sine of pi over 2 is 1. 4 times 1 is 4. If t is pi over 2, 2 times pi over 2 is pi. Sine of pi is 0. 4 times 0 is 0. If t is 3 pi over 4, 2 times 3 pi over 4 is 3 pi over 2. Sine of 3 pi over 2 is negative 1. And 4 times negative 1 is negative 4. And if t is pi, sine of 2 pi will be 0. 4 times 0 is 0. Now for y, you're using the parametric equation y is equal to 2 times cosine of 2t. So if t is equal to 0, then you have 2 times 0, which is 0. Cosine of 0 is 1, and 2 times 1 is 2. If t is pi over 4, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. 2 times 0 is 0. And then if t is pi over 2, 2 times pi over 2 is pi. Cosine of pi is negative 1. 2 times negative 1 is negative 2. And then we have, if t is 3 pi over 4, then 2 times 3 pi over 4 will be 3 pi over 2. Cosine of 3 pi over 2 is 0. 2 times 0 is 0. And if t is pi, 2 times pi is 2 pi. Cosine of 2 pi is 1. 2 times 1 is 2. So you can take these ordered pairs and you can plot them, and that will give you the graph of the set of parametric equations that we have. So we will begin by plotting the point 0, 2. So we have 0 for x and 2 for y, and this happens when t is equal to 0. And then we have the point 4, 0. This happens when t is equal to pi over 4. We have the point 0, negative 2. This happens when t is equal to pi over 2. We have the point negative 4, 0. This happens when t is equal to 3 pi over 4, and we have the point 0, 2. Once again, we're back where we started at t is equal to pi. So if you trace the curve following increasing values of t from 0 to pi, you would start here and you would go clockwise, and the curve that is traced is in fact an ellipse. So you can indicate the orientation of the curve by drawing arrowheads, or you can write the word clockwise. So how do we do this using Desmos? So let's take a look at that. Number 23 is similar to number 21. We're also going to use the Pythagorean identity sine squared t plus cosine squared t is equal to 1 to help us eliminate the parameter t in our set of parametric equations. And the reason why you might think that is because you see both cosine and sine functions as a part of your parametric equations. So before you can square to get cosine squared t and sine squared t, you should isolate the trig expressions cosine t and sine t in each parametric equation. So in the first one, you can begin by subtracting 4 from each side of the equation, and in the second one you can begin by adding 1 from each side of the equation. So in the first equation you also have to divide both sides of the equation by 2 to get x squared, x minus 4 divided by 2 is equal to cosine t. So now you have isolated the trig expressions, so you can square each side of each equation. So you will get x minus 4 squared over 2 squared is equal to cosine squared t, and y plus 1 squared is equal to sine squared t. So having done that, what are you going to do now? You're going to use the Pythagorean identity. So we have sine squared t plus cosine squared t, or you can also write cosine squared t plus sine squared t is equal to 1. So cosine squared t, you can substitute for cosine squared t with x minus 4 squared over 4. And you can substitute for sine squared t with y plus 1 squared over 1, if you'd like to write that, and that would be equal to 1. So this is the rectangular equation. The parameter t has been eliminated, and this is also an equation for an ellipse. But unlike number 21, where our ellipse was centered at the origin, in this problem our ellipse is centered at the point 4, -1. And then you can examine this rectangular equation to determine the length of both the major and the minor axes. And you can also plot points. One way to easily find 4 points on your ellipse is to choose a value of x that would make this term equal to 0 and solve for y. So you can choose x to be 4 and you can solve for y. And you can find 2 additional points by choosing a value of y that would make this term equal to 0 and solve for x. So you can choose y to be -1 and solve for x. I will also have how to do this using Desmos, using a graphing utility to graph this curve, but we're expecting an ellipse and indicating the orientation. We'll see that when we do this using Desmos. So here we take a look at number 31, and we want to eliminate the parameter and write the corresponding rectangular equation. So the 2 previous problems, we used the Pythagorean identity sine squared t plus cosine squared t is equal to 1. A more standard approach is to solve for t in one parametric equation and substitute for t in the other equation. So what we do in this particular problem is closer to the standard approach, but we're not going to be solving for t because it's not necessary, because you'll notice something about these 2 parametric equations. In both of them, you have e to some power. So you have e to the -t, which is equal to x, and e to the 3t, which is equal to y. So here's what we're going to do. We're going to rewrite the parametric equation for y using a property of exponents. So if you have e to the t to the 3rd, you have the power of a power. And when you have the power of a power, you multiply the exponents. T times 3 will give you 3t. Now, this one here, you're going to write this as e to the -t using properties of exponents. You can write that as 1 over e to the +t. One thing that you might notice is that in both of these equations, I have e to the t. So we're going to take advantage of that. So we don't have to solve for t completely. It's enough for me to just solve for e to the t. And we can solve for e to the t in the first equation as follows. Multiply both sides of the equation by e to the t, and then divide both sides of the equation by 1 over x. And now I can take this and substitute for e to the t in the other parametric equation, and I get y is equal to 1 over x to the 3rd power. So you can see that I was able to successfully eliminate the parameter because I no longer have t, and I'm done with eliminating the parameter. And this is the corresponding rectangular equation. Again, I will go ahead and use Desmos to show you what the curve would be. When we graph it using Desmos, we can also see the orientation of the curve. Today we looked at eliminating the parameter in a set of parametric equations, and we also looked at using Desmos to graph the curve represented by a set of parametric equations.